Hi guys, today we're going to cover similar figures, specifically Triangle Proportionality Theorem. First I'll show you what Triangle Proportionality Theorem is, then we'll cover 4 examples. So let's get started. In the previous video on proportional polygons, I talk about triangles that are proportions and how to set up a proportion. All a proportion essentially is a fraction equal to a fraction. In this case, just for some quick review, I could set something up like 3 over 9, 5 over 15. I can cross multiply and get 45 equals 45. Or I could take that fraction that I had and I could reduce them both to get the same answers. And those are proportions. What your triangle proportionality theorem states is that I could take this triangle and place it on top of this one, creating a set of parallel lines. What ends up happening is this length here is 10 and this length here is 6. I got those by just subtracting 15 minus 5 and 9 minus 3, and I still have proportions. So for example, I could set this up 3 over 9, which is what I did before, 5 over 15, or I could set this up 3 over 6, which is equal to 5 over 10. And in both cases, I will get equal fractions on each side. The other way to look at it, once again, is to cross multiply. 3 times 10 is 30, times 5 is 30. So essentially, a derivative of separate proportional triangles. Alright, let's take a look at a couple of examples. This is a simple proportional triangle. In fact, it's one that you're more likely to encounter in the real world. But remember, simple does not mean easy. We have to take that out of our association of vernacular. So here, simple typically is pretty difficult for students. In fact, this is a problem that my students tend to have quite frequently. And I get a lot of questions on this problem. For starters, I want to find this side here where the question mark is, so I'm going to turn that into an X because that's just what we're used to seeing. I have to set up a proportion. The problem is if I set this up X to 14, kind of the way I did on the previous example, I can't do that here because I have nothing here. So what I need to do is I need to subtract 7 minus 4 to get 3. That gives me 3 here. So now I kind of have the sides to the small triangle, and I could set that up. Then I could cross multiply and solve. So this is going to be 7x is equal to what looks like 42. And then I divide by 7 on each side, and x equals 6. Most students navigate this part pretty well once they see it. But the difficulty is this primary setup, which requires a reasonable understanding of proportions. Alright, let's take a look at an example that's pretty commonly presented in these math curriculums. This time, I'm presented with an expression here, which is a little bit more common, but the rules don't change. I have 2 options, and I want to explore both those options here. The first is I could add this side, which is a little bit tricky if we don't have good control of our arithmetic rules. To add those sides, I would have to say x plus 13 plus 15, which gives me x plus 28. I can then set this up using this x plus 28 here, and I will get the same answer. My opinion is that's a little bit more difficult, so I'm going to try to avoid that when I look on this side here and notice that I have 28 and 12. Those are significantly easier numbers to subtract. 28 minus 12 is 16. Now I could use all these sides here that I have, so these correspond and these correspond, and from there I could set up a proportion. Let me color code this so I can make it a little bit clearer. So I have a number of ways I could set this up, and again I presented that in the previous video. What I'm going to do here is I'm going to take the time to consider what the easiest way is to set this up. Well, I'm not really that comfortable with 16 times tables, it turns out. So what I want to do is try to reduce that. So I'm going to place that on top here, and that is a small triangle. So that means on the other side, I have to place that on top. Now what I'm going to do is place the part of the large triangle under it, and that would look something like this. It's a little bit simpler to solve. If you're struggling with these setups, that is okay, but take a second and recognize how I set up this proportion and observe that pattern. So now I'm going to go through the steps, take the steps I'm trying to say to cross multiply this or to solve it. The first thing I'm going to do is reduce this fraction to make this a whole lot easier on myself. One of the nice things about solving proportions in this context is that I could take the time to try to figure out how to make the problem easier for myself. I almost typoed here. Again, I actually had to redo this problem because of that typo. Now, I am going to cross multiply, so that is 60. This is headed this way, which is 3x plus 39. I'm going to subtract the 39, and I'm going to get 21. That's an equal sign, so let's not lose that. And now what I'm going to do is divide by 3, and x is equal to 7. In the previous video that I'm sure I have linked at this point to this video, I go through the solving steps in detail. Now, I want to take a second and show you how I discovered my previous error that I had cut out of this video. If you're not interested, you could just skip to the next example, which I have timestamped. When I originally did this problem, I got 17 because of that typo that I corrected. So I went through the whole problem solving it x plus 3. What I did is I then took it and plugged it into here, this side, which in this case gives me 20. I tested the proportion, which I'm going to do now. So the length of this side here is actually 20. And that's the whole point of proportions, by the way, is to kind of figure out how these different shapes that are similar fit together. When I set up the same proportion that I did to solve the problem, I cross-multiplied and got a different answer. But in this case, it's going to work out to be the same thing, as long as I don't flip that side, which I almost just did again. So this reduces to 4 over 3, and that reduces to 4 over 3. Or, when I cross multiply, I get 240 on each side of the equal sign. Do I recommend doing this check? You can. It's not like other checks when we solve for x. In this case, the proportion won't physically work, so you could always check yourself that way. Alright, let's take a look at the next example. A ramp which extends 10 meters from the base of a building is 6 feet high. How many feet longer would you need to make the ramp to go 8 feet high? This is a real-world application of proportions. How many people actually do this? I don't know, but it will work if you're in this scenario. Now, here is the problem. The problem is, I do not have these lengths here. They're missing. So the way I have to set up the proportion is from this direction. So I have to set up 10 over 6. Okay, that leads to a bit of an issue, because this piece here is not proportional with 10. So x is not proportional with 10. And the reason being is, this is the small triangle, so I'll do something like this and something like that. Then this is a large triangle here. So I have to create a large triangle. The way I could do that is I can add this side, creating the length of the side for the large triangle. We cannot compare unlike parts in a proportion. That's the purpose of it. Proportions can only compare apples to apples and oranges to oranges to get things to work. You cannot compare apples to oranges, which would have been that case. So now I am going to set this up. If I put 10 on top here, I have to put 10 plus x over 8 here. Again, take a second before maybe even shooting forward and observe the pattern. I'm not suggesting to stare at the screen paused for 20 minutes, but just take a second and understand how this proportion was set up. Alright, now that you've done that, I'm sure you have, I'm sure you paused this for a long time to consider that pattern, I am going to reduce this problem to 5 over 3, then 10 plus x over 8, and now I'm going to cross multiply. So that's 40, I have the 3 here, 10 plus x, then distribute here, so I get 30 plus 3x, then I subtract by 30, I subtract by 30, and 10 equals 3x, then I divide by 3, and the answer is, as far as I am concerned, 10 over 3x. If I need to, I will convert that to a decimal and try to line it up to a measuring tape or whatever measuring utensil I am using to get that length. But for the purpose of this problem, 10 over 3 is just fine. Okay, let's take a look at the next example. A man 6 feet tall casts a shadow that is 11 feet 6 inches long. The end of his shadow coincides with the end of the shadow cast by a building 128 feet from the man. Find the height of the building. Explain how you found your answer. Okay, this is a standardized test question, I believe. The other thing to know is that this is really not real-world application of this math, but you can use it to do this. I have personally used this math to figure out the height of trees, so when I cut them down, I make sure I don't hit my house. This, along with trigonometry, which will come in later videos. Alright, we have the same problem in this example as I did in the previous one, but there's a little wrinkle here. And frankly, I think it's kind of a dirty little trick. 11 feet 6 inches is not 11.6. It is 11.5. 11.6 is incorrect because 6 inches is a half a foot, not 0.6 of a foot. Remember, there are not 10 inches in a foot, there are 12. Changing that decimal and it can change your answer, leading to the wrong answer. So if this was a multiple choice question, the answer for 11.6 would be waiting for you, which again I think is a slightly dirty trick because you could understand how to do proportion, but you forget in your haste or just don't know, if you always work with the metric system, that 6 inches is half a foot. It's one of those things that I think are very easy to overlook, so be careful when approaching these problems. But otherwise, now that that rant is over, we're going to solve this problem the same way I did before. I'm going to add this side here, and I'm going to cross multiply and solve. I'm not a huge fan of decimals because now I have to rely on a calculator and I cannot reduce this problem. So since I set this up 11.5 over 6, I'm going to set this up 139.5 over x. And I'm going to use my calculator to multiply 6 times 139.5 to get 837, which is nice. That kind of cleared itself up, but I still have the 11.5 times x. Then 11.5, I'm going to have to divide that out. In my opinion, and this is just my opinion, I'm not saying it's worth much, I would have preferred this problem to be in the form of a fraction. Let's say 23 over 2, and that would have made the problem easier. But we also have to be limited to the height or the constraints of our world. Something's wrong here because that building's only 7 feet, 0.2, which doesn't make sense. And the reason for that is, I'm not going to cut this mistake out, is when I punch it in the calculator, in all my rambling, the decimal point did not make it. There we go, 72 feet. That makes a whole lot more sense. 0.78. Again, another case why I'm not a huge fan of decimals, but it's very easy to typo them. Okay, guys, I hope you have found this video on Triangle Proportionality Theorem helpful.